Headlines about quantum computers sound almost mythical. The promise is enormous. Machines that can shatter modern encryption, systems that can solve problems no classical computer could ever finish, devices powerful enough to model nature at the deepest level. Governments are investing billions. Technology companies are racing to build the first truly useful quantum machine. Every few months, a new announcement appears claiming a breakthrough that will change the future of computing forever. The story feels unstoppable, a technological revolution unfolding in real time. But beneath all the excitement, inside physics labs and research papers, a quieter conversation is taking place. Many scientists say the public story of quantum computing is running far ahead of the science itself. The hype is loud, the reality is far more complicated, and the gap between those two worlds is one of the most fascinating stories in modern science. Quantum computing is often presented as the ultimate upgrade to the computers we use today. A leap so large that it could redefine technology, economics, security, and scientific discovery. In theory, these machines use the strange rules of quantum physics, rules where particles can exist in multiple states at once, and distant objects can remain mysteriously connected. Those rules open the door to new kinds of calculations that classical computers struggle with. This idea alone sparked enormous excitement. If quantum mechanics governs the smallest pieces of nature, then a computer built on those rules might unlock problems that were previously impossible. Problems in chemistry, medicine, materials science, and cryptography. For a moment, it seemed as if a completely new computational universe had appeared. That vision spread quickly. Articles predicted the end of modern encryption. Some claimed quantum computers would break internet security in minutes. Others said artificial intelligence would accelerate beyond anything seen before. Investors poured money into quantum startups. Governments began national quantum programs. Tech giants started building experimental machines. The narrative became powerful and simple. Quantum computers would soon outperform classical computers at almost everything. A revolution was coming, and it was just around the corner. But inside research labs, the situation looked very different. Building a quantum computer is one of the most difficult engineering challenges humans have ever attempted. The basic units of quantum information, known as qubits, are incredibly fragile. Tiny disturbances from the environment can destroy their quantum behavior in an instant. Heat, vibration, radiation, even the smallest electrical noise can collapse the delicate quantum state. Keeping qubits stable requires extremely controlled conditions. Some machines operate only a fraction of a degree above absolute zero, colder than outer space. Others trap ions in electromagnetic fields with astonishing precision. Every qubit must be isolated from the outside world while still being controlled by complex electronics. It is a balancing act that pushes technology to its limits. Even when researchers manage to control qubits, another obstacle appears: errors. Quantum systems are noisy by nature. Calculations can easily drift off course because of tiny imperfections in the hardware. To build a truly reliable quantum computer, scientists must develop sophisticated error correction methods, and those methods require far more qubits than the small experimental machines we have today. In some cases, thousands of physical qubits may be needed to produce a single stable logical qubit that can perform accurate computations. This scaling challenge means that the powerful quantum computers, often described in headlines, are still far in the future. That contrast between expectation and reality is the heart of the story. Quantum computing is not fake science. The physics behind it is real and deeply fascinating. Researchers are making steady progress every year. New qubit designs are being tested. Error rates are slowly improving. Experimental devices continue to grow in size and complexity, but the technology is still in an early stage. Many experts describe today's machines as experimental tools rather than practical computers. They are remarkable scientific achievements, yet they are far from replacing classical computers. This gap between promise and progress raises an important question. If the science is real, why does the hype grow so quickly? Part of the answer lies in the nature of technological revolutions. Every major breakthrough begins with bold ideas and ambitious predictions. Early aviation promised effortless flight across the globe, long before airplanes were reliable. Artificial intelligence experienced waves of excitement and disappointment for decades before modern breakthroughs arrived. Quantum computing may be following a similar path, a mixture of genuine discovery, hopeful speculation, and intense competition. Another reason is the strategic importance of quantum technology. Governments see it as a potential advantage in security and scientific leadership. Companies see opportunities for new industries. Investors see the possibility of a trillion-dollar market. When so many powerful forces focus on a technology, the story surrounding it can grow faster than the science itself. The result is a world where quantum announcements appear dramatic and revolutionary, even when the underlying progress is incremental. This does not mean the field lacks real achievements. Over the past few years, researchers have demonstrated quantum processes with dozens and even hundreds of qubits. Experiments have shown specialized quantum calculations that classical computers struggle to reproduce. Scientists are exploring new algorithms designed specifically for quantum machines. Entire research communities are working to solve the enormous challenges that remain. Progress may be slower than headlines suggest, but it is steady and meaningful. That is why understanding the difference between quantum hype and quantum reality matters. Without that distinction, the public conversation becomes distorted. Expectations rise too high. Disappointment arrives too quickly, and the real scientific story gets lost. The true journey of quantum computing is not a sudden revolution, but a long process of discovery. A process that reveals both the astonishing power of quantum physics and the immense difficulty of turning theory into technology. This video will guide you through that journey. You will learn what quantum computers actually are and why their design is so different from classical machines. You will see where the biggest hype comes from and why some claims about quantum technology are exaggerated. You will also discover the genuine breakthroughs that scientists are working toward and the areas where quantum computers might one day provide real advantages. By the end, the confusing landscape of quantum headlines will start to make sense, and the line between speculation and science will become much clearer. The goal is not to dismiss the excitement surrounding quantum computing. The field is one of the most ambitious scientific efforts of our time. Instead, the goal is to uncover the real story hidden behind the dramatic claims. A story of fragile qubits, extreme engineering challenges, and patient research. A story where progress happens step by step rather than overnight. And a story that reveals how science truly advances through careful experiments, unexpected setbacks, and persistent curiosity. So stay with this video until the end, because the truth about quantum computing is far more interesting than the headlines alone. The reality is deeper, more complex, and in many ways more exciting than the hype that surrounds it. Welcome to the channel. If you enjoy exploring the real science behind big ideas and cutting through the noise to understand how the universe actually works, make sure to subscribe and join us as we continue to explore the fascinating frontier where physics, technology, and the future meet. Quantum computing stands at the center of one of the most intense technology conversations in the world today. Every major scientific conference, technology summit, and research lab seems to return to the same topic again and again. Governments are funding massive research programs. Technology companies are building experimental machines. Universities are training a new generation of physicists and engineers to work on quantum systems. The attention is enormous because the potential impact appears enormous. The idea of a completely new kind of computer naturally attracts excitement. But beneath all the excitement lies a deeper question that quietly shapes the entire field. The real question is not simply whether quantum computers are interesting or powerful. The real question is whether the world is standing at the beginning of a true technological revolution, or whether much of the excitement surrounding quantum computing is running far ahead of what science can currently deliver. This question divides opinion among experts, investors, engineers, and policymakers. Some see quantum computing as the next great leap in human technology, a tool that could unlock scientific discoveries that classical machines cannot even approach. Others see a technology that is promising but still extremely immature, surrounded by bold predictions that may take decades to become real.
The only way to understand this situation is to separate two ideas that are often mixed together in public discussions. One is quantum hype, the other is quantum reality.
To understand that difference, it helps to begin with the most basic question. What exactly is a quantum computer? The computers used every day, from phones to laptops to massive data centers, all follow the same fundamental logic. They store and process information using units called bits. A bit is extremely simple. It can represent one of two states, 0 or 1. Every piece of information processed by a classical computer eventually reduces to long strings of zeros and ones. These bits are manipulated through logical operations performed by transistors, tiny electronic switches that turn on or off depending on electrical signals. Over the past 70 years, engineers have learned to pack billions of these transistors onto a single chip, allowing computers to perform astonishing numbers of calculations every second. Classical computers are incredibly powerful tools, but they follow strict rules. At any given moment, each bit is either 0 or 1. There is no middle state and no overlap between the two possibilities. Quantum computing introduces a completely different way of representing information. Instead of bits, quantum machines use units known as qubits. The word qubit simply means quantum bit. But the behavior of a qubit is very different from that of a classical bit. A qubit can exist in a condition called superposition. In this state, the qubit does not hold a single definite value like 0 or 1. Instead, it can exist in a combination of both states at the same time. The mathematics of quantum mechanics allows a qubit to represent a mixture of 0 and 1 simultaneously until it is measured. When scientists first realized this property could be used for computing, it opened a door to an entirely new form of information processing. Superposition becomes even more interesting when multiple qubits interact with each other. Quantum systems allow another strange property called entanglement. When qubits become entangled, the state of one qubit becomes deeply connected to the state of another, even if they are separated in space. Their properties cannot be described independently anymore. They behave as parts of a single combined system. This connection allows quantum computers to process information in ways that do not exist in classical computing. Instead of evaluating possibilities one at a time, a quantum system can explore many possibilities at once through carefully designed quantum operation. This strange behavior led scientists to a powerful idea. Certain problems in mathematics, chemistry, and physics might be solved much faster using quantum machines than classical computers. In particular, problems that involve enormous numbers of interacting possibilities may benefit from quantum computation. For example, molecules are governed by quantum mechanics at the atomic level. Simulating the precise behavior of complex molecules on a classical computer quickly becomes extremely difficult because the number of interactions grows rapidly as the system becomes larger. Quantum computers, in theory, could simulate these systems more naturally because they themselves follow the same quantum rules. This realization triggered enormous excitement when it first appeared in the scientific community. The possibility of using quantum machines to solve problems that classical computers struggle with seemed revolutionary. Researchers began developing theoretical algorithms that could exploit the properties of qubits, superposition, and entanglement. One famous algorithm showed that a sufficiently powerful quantum computer could factor very large numbers far more efficiently than classical machines. Since modern encryption systems rely on the difficulty of factoring large numbers, this discovery suggested that quantum computers might one day break widely used security protocols. Suddenly, the technology was no longer just an academic curiosity. It became a strategic issue for governments and industries around the world. As the scientific ideas spread beyond physics departments and into the broader technology world, excitement grew rapidly. The narrative became simple and dramatic. Quantum computers would soon outperform classical computers. They would solve problems that were previously impossible. They would revolutionize fields ranging from cryptography to artificial intelligence. Technology companies began building early prototypes. News headlines began celebrating each new milestone. Investors began funding startups promising future quantum breakthroughs. But this is where the first layer of hype begins to appear. Many popular descriptions of quantum computing give the impression that these machines will eventually replace classical computers entirely. The suggestion often appears that quantum systems will be able to solve almost any problem instantly once they become large enough. Some descriptions go even further and imply that quantum computers will transform every area of technology. These claims create the impression that quantum machines are simply faster versions of classical computers, capable of doing everything better. The reality is very different. Quantum computers are not universal supercomputers designed to replace classical machines. They are specialized tools built for specific types of calculations. For many everyday tasks, classical computers remain far more efficient and practical. Simple operations such as running word processors, browsing the internet, managing databases, or performing most business computations do not benefit from quantum algorithms. Classical machines are optimized for those tasks and will continue to perform them far more efficiently than quantum devices. Quantum computers become interesting only for particular categories of problems where quantum effects provide a computational advantage. Even in those cases, the advantage depends on carefully designed algorithms that exploit the unique behavior of qubits. Without the right algorithm, a quantum computer may not perform better than a classical machine at all. This means the power of quantum computing is not universal. It is selective. It depends on the structure of the problem being solved. Another layer of hype surrounds the idea that quantum computers will immediately break all encryption systems used on the internet. While it is true that certain quantum algorithms could eventually threaten some current cryptographic methods, practical quantum machines capable of performing those calculations are still far beyond the scale of existing devices. Researchers are also developing new forms of encryption designed specifically to resist quantum attacks. Security experts are already preparing for this possibility, which means the transition to quantum-resistant cryptography will likely occur long before large-scale quantum attacks become feasible. Claims that quantum computers will power super-intelligent artificial intelligence also appear frequently in popular discussions. While quantum algorithms may someday assist certain machine learning tasks, there is currently no evidence that quantum computing will automatically lead to dramatic improvements in artificial intelligence. Most AI systems rely on massive amounts of data processing and statistical optimization, areas where classical computing remains extremely effective. Understanding the limits of quantum computing requires looking closely at the physical challenges involved in building these machines. Quantum systems are extremely delicate. The very properties that make qubits powerful for computation also make them incredibly fragile. A qubit must maintain its quantum state long enough to perform calculations, but interactions with the surrounding environment can quickly destroy that state. This problem is known as decoherence. Even the smallest disturbance can collapse the superposition of a qubit and eliminate the quantum advantage that researchers are trying to use. To protect qubits from environmental interference, quantum computers often operate under extreme conditions. Some systems are cooled to temperatures just above absolute zero using complex refrigeration equipment. Others trap individual atoms or ions inside electromagnetic fields within high vacuum chambers. These environments reduce unwanted interactions, but they also make the hardware extremely complicated and expensive to maintain. Noise is another major challenge. In quantum computing, noise refers to random disturbances that alter the behavior of qubits during calculations. Unlike classical computers, where bits are stable and predictable, qubits are inherently sensitive to small fluctuations. These fluctuations introduce errors into quantum operations. A single incorrect operation can distort the entire result of a quantum computation. Because of this, error correction becomes essential for building reliable quantum machines. Classical computers also use error correction, but the process is relatively straightforward because classical bits are easy to copy and verify. Quantum information behaves differently. The laws of quantum mechanics prevent qubits from being copied directly in the same way classical bits can be duplicated. This means quantum error correction requires complex schemes that distribute information across multiple physical qubits. In practice, this means that building a single reliable logical qubit may require hundreds or even thousands of physical qubits working together. When researchers talk about quantum computers with dozens or hundreds of qubits today, they are usually referring to physical qubits that still experience significant noise and error. Creating large numbers of stable logical qubits remains one of the central challenges of the field. Scaling the technology introduces additional difficulties. Building a small experimental quantum processor with a few qubits is already a significant achievement. Expanding that system to thousands or millions of qubits requires entirely new engineering solutions. Each qubit must be controlled precisely while remaining isolated from unwanted interactions. The wiring, cooling systems, control electronics, and error correction mechanisms all become more complex as the system grows. Because of these challenges, the current generation of quantum computers is often described as belonging to the NISQ era. This term stands for Noisy Intermediate Scale Quantum. It reflects the fact that existing machines are still relatively small and contain significant levels of noise. These devices are powerful research tools used to explore quantum algorithms and hardware designs, but they are not yet capable of solving large practical problems that would transform industries. Despite these limitations, researchers remain optimistic about the long-term potential of quantum computing. The technology may not revolutionize every area of computing, but it could provide powerful advantages in specific fields where quantum systems naturally play a role. Chemistry is one of the most promising examples. Chemical reactions depend on the behavior of electrons and atoms, which are governed by quantum mechanics. Simulating these interactions accurately requires enormous computational resources when using classical computers. Quantum machines could potentially model these systems more efficiently, allowing scientists to design new materials or drugs with greater precision. Materials science is another area where quantum simulation could become valuable. Discovering new materials with unusual electrical, magnetic, or structural properties often requires exploring complex quantum interaction. Quantum computers may eventually help researchers explore these interactions directly, accelerating the development of technologies such as better batteries, superconductors, or energy storage systems. Optimization problems also attract attention in the quantum computing community. Many industries face complex decisions that involve finding the best solution among a huge number of possibilities. Logistics networks, financial portfolios, manufacturing processes, and communication systems all involve optimization challenges. Some quantum algorithms may provide advantages for specific optimization tasks, though researchers are still investigating when and how those advantages will appear in practice. Quantum physics itself may benefit from quantum computers as well. Understanding the behavior of complex quantum systems is extremely difficult using classical simulation methods. A quantum computer built from interacting qubits could serve as a platform for exploring new physical phenomena and testing theoretical models. In this sense, quantum computers might function not only as calculation tools, but also as experimental laboratories for studying the fundamental laws of nature. The gap between hype and reality also reflects the powerful forces driving investment in the field. Quantum technology has become a global priority for many governments. Countries see leadership in quantum computing as a potential strategic advantage in science, security, and industry. National research programs now fund large teams of scientists working on quantum hardware, algorithms, and communication systems. Competition between major technology companies adds another layer of momentum. Companies want to be the first to demonstrate a practical quantum advantage because that achievement could reshape the future computing landscape. As a result, announcements about new quantum processes or experimental milestones often receive enormous attention. These announcements can sometimes appear more dramatic than the underlying progress actually represents. Marketing also plays a role in shaping the public perception of quantum computing. Startups seeking investment often highlight the most ambitious possibilities of the technology. Large companies emphasize breakthroughs that demonstrate leadership in the field. Media coverage tends to focus on bold predictions and dramatic narratives rather than slow technical progress. This combination creates a cycle where expectations rise rapidly, even when the science advances gradually. History shows that many transformative technologies experience similar cycles of excitement and adjustment. Artificial intelligence passed through several waves of intense optimism, followed by periods of slower progress. The early internet inspired both visionary predictions and exaggerated claims before its true impact became clear. Blockchain technology also generated enormous hype before its practical uses began to settle into more realistic expectations. Quantum computing may be following a comparable path, where enthusiasm pushes exploration forward, while reality gradually shapes the final outcome. Amid all the speculation, genuine scientific progress continues to unfold. Researchers around the world are developing new qubit technologies using superconducting circuits, trapped ions, photons, and other physical systems. Each approach has its own strengths and challenges. Some offer high precision but limited scalability, while others promise easier scaling but face greater noise problems. Exploring these designs helps scientists learn which architectures might eventually support large-scale quantum machines. Quantum algorithms are also improving. Early algorithms focused mainly on theoretical demonstrations of quantum advantage. More recent research explores hybrid approaches where quantum processors work alongside classical computers. In these systems, classical algorithms perform most of the computation, while quantum circuits handle specific subproblems where quantum effects may provide benefits. This combination could allow useful applications to emerge even before fully error-corrected quantum computers become available. Error correction techniques continue to evolve as well. Researchers are developing new codes that distribute quantum information across many qubits in ways that protect against noise. These methods require complex hardware and control systems, but steady progress is being made. Demonstrations of small error-corrected qubit systems have already appeared in laboratories. Expanding these systems remains difficult, but each experiment brings scientists closer to understanding how large-scale quantum machines might eventually operate. Hardware improvements also occur year by year. Qubit coherence times, which measure how long a qubit can maintain its quantum state, have steadily increased in many systems. Control electronics have become more precise. Fabrication techniques for superconducting circuits have improved. Trapped ion systems now manipulate strings of atoms with extraordinary accuracy. Photonic quantum systems explore entirely different approaches using particles of light. Each of these developments contributes small but meaningful steps toward more capable quantum processes. When viewed from a historical perspective, quantum computing today resembles the early stages of aviation more than the modern airline industry. Early airplanes demonstrated the basic possibility of flight, but struggled with reliability, power, and control. It took decades of experimentation before aircraft became practical tools for transportation and commerce. Quantum computing may follow a similar timeline, where fundamental breakthroughs gradually transform experimental devices into useful technologies. The most important insight emerging from this story is that quantum computing is neither pure hype nor an instant revolution. It represents a long process of scientific exploration. The field combines deep theoretical physics with extremely demanding engineering. Each improvement requires careful experimentation and incremental learning. Progress may appear slow compared to the dramatic predictions that often appear in headlines, but steady progress is the normal pattern of scientific discovery. Over the coming decades, quantum computers may become valuable instruments for solving certain classes of problems that classical machines struggle with. They may help scientists understand complex molecules, design new materials, or explore quantum physics itself. These achievements could transform specific areas of science and technology, even if quantum computers never replace classical machines entirely. The future of quantum computing is therefore not a story of magical devices that instantly solve every problem. It is a story of new tools, gradually expanding the boundaries of human knowledge and capability. Quantum computing stands at a strange crossroads in the history of science and technology. On one side, there is a powerful dream. A dream of machines that could process information in ways no classical computer ever could. a dream of solving problems so complex that they once seemed permanently beyond human reach. That dream fuels enormous excitement. It drives governments to invest billions. It pushes companies to build experimental machines. It inspires scientists to explore one of the deepest frontiers of physics. The promise is bold and fascinating, a completely new way of computing, built from the strange rules of the quantum world. But on the other side, there is a much quieter reality, the reality of fragile qubits that can lose their quantum state in an instant, the reality of error rates that researchers are still struggling to control, the reality of machines that must operate in extreme conditions just to function for a few moments. Building a quantum computer is not simply an engineering project. It is a battle against nature itself, against noise, instability, and the delicate laws of quantum mechanics. Progress exists, but it moves carefully and slowly, one experiment at a time. And somewhere between these two extremes lies the real story of quantum computing. Not a magical machine that instantly replaces every computer on Earth. Not an empty promise that disappears after the hype fades. Instead, it is something far more interesting. Quantum computing is a scientific journey, a journey that is still unfolding. Every year, researchers learn a little more about how to control quantum systems. Every year, new ideas appear for algorithms, hardware designs, and error correction. The machines grow slightly larger, slightly more stable, slightly more capable. Step by step, experiment by experiment, the technology moves forward. History shows that many of the most powerful inventions in human history began this way. The first airplanes could barely stay in the air. The first computers filled entire rooms, yet performed fewer calculations than a simple phone today. The first rockets struggled to reach space. At the beginning, every revolutionary technology looks fragile, complicated, and uncertain. Only time, persistence, and thousands of small improvements turn those early experiments into tools that reshape the world. Quantum computing may follow the same path. It may not transform everything overnight. It may not instantly break every encryption system or solve every scientific mystery. But over time, it could become something incredibly valuable, a new scientific instrument, a tool that helps scientists explore the behavior of molecules, design new materials, understand complex quantum systems, and uncover patterns that classical computers cannot easily reach. In that sense, quantum computers are not replacements for classical machines. They are companions to them, different tools for different kinds of questions. The most fascinating part of this story is that it is still being written. Laboratories around the world are working every day to push the limits of what is possible. Engineers are designing new qubit technologies. Physicists are discovering better algorithms. Entire teams are focused on solving the noise and error problems that stand in the way of large-scale machines. The future of quantum computing will not arrive through a single dramatic breakthrough. It will arrive through thousands of careful steps taken by researchers who refuse to give up on one of the most challenging problems in modern science. So when you hear bold headlines about quantum computers changing everything tomorrow, remember the deeper truth. The real revolution in science rarely happens overnight. It grows slowly through curiosity, patience, and relentless experimentation. Quantum computing is part of that long tradition, a bold attempt to harness the strange rules of the universe and turn them into tools for discovery. In the end, quantum computers sit between imagination and reality. They are not science fiction anymore, but they are not miracles either. They are simply the next step in humanity's long effort to understand the universe and use that understanding to build something new. If you enjoyed exploring the real story behind quantum computing and want more videos that uncover the science behind big ideas, make sure to subscribe to the channel. Also, leave a like if you found this video interesting and share it with someone who loves science and technology. Your support helps the channel continue creating deep and fascinating content like this. And until the next video, keep asking questions, keep exploring, and keep looking beyond the hype to discover the reality hidden inside the science.